When we think about molecules, one of the things we're always considering is where are the electrons being pulled to? Where's the greatest density of electrons? So to understand that, we got to talk a little bit about electronegativity. Now, admittedly, you probably did a lot of this in Orgo, and you're probably pretty masterful with thinking about this in terms of the trend on the periodic table. So we're just going to go a little bit deeper in this course so that we can see that, hey, we don't just have to look at it qualitatively. There actually are quantitative scales. For most purposes, knowing the trend is important. So recognizing the most electronegative are up here in the upper right-hand corner, whereas the least electronegative atoms are down here in the lower left. And remember, this is just the ability to pull electrons towards the atom. So it says that, hey, on average, a fluorine atom is going to be really pulling electrons towards itself, whereas something like cesium down here in the lower left would not. And yeah, we use that in Orgo all the time. Physical chemists came up with some more detailed understandings of this, specifically starting with Linus Pauling back in the 30s, where they made the observation that a covalent bond between two different atoms is stronger than the homonuclear version of this. So AA or BB would have a bond between them, but it would be stronger if there was an AB bond. Which was kind of interesting. So from this and using a lot of experimental data, he started working out a theory. His thought that he could use this to say is, hey, this is what they call electronegativity, and it's really telling us something about the ionic character of that bond. We recognize that as we are getting more and more electronegative, we're pulling electrons harder and harder away from something, getting closer to full electron transfer, which is ionic. So Pauling used this thought to define his own system for defining electronegativity. He said, well, we can measure the dissociation energy of AB, and by this I mean we've got a bond between A and B, so how much energy does it take to break that bond? Well, from that, we could also use the dissociation energy of both of the homonuclear diatomics here and say how much energy is required to break those. Let's add those together up. Find the average of that by dividing by 2, and then add on this quantity, chi A minus chi B squared, where these chi terms are the Pauling electronegativities. Now, the thing to notice here that we have two unknowns here. We do not know what chi A is. We do not know what chi B is. So there's no way to actually put this to a numerical scale. Therefore, it is a relative scale. It only compares the differences between the electronegativity for those two atoms. But 1930s, this was the data we had, this was the understanding we had, and it worked for the most part. Next person on our rotation here on electronegativity was Mulliken. Mulliken's a scientist you probably haven't heard much about, but was a major player in physical chemistry in the 20s, 30s, and 40s. Electronegativity, he said, was the tendency to gain and lose electrons. Therefore, it makes sense that this should be connected to the ionization and the electron affinity. So we talked about those atomic properties earlier. This is how easy is it to gain, how easy is it to lose an electron. So Mulliken said, hey, if we want to define the electronegativity, again using the term chi here, we should just look at the sum of the ionization and the electron affinity of that atom and then divide it by 2. So really this is just an arithmetic mean of the ionization energy and electron affinity. It's just that. There's not a whole lot more to it to describe any of the subtleties here. But it does give us now an absolute scale for every atom. Again, was it perfect? Not really. But did it do a good function where now we have something that we can quantify? Yes, indeed it did. Probably the most recent change to electronegativity and how we could calculate it was by Allred and Rochot, that are modern scientists. These came up with their modern, and I'm talking about 1958. That's kind of hilarious. So this is our modern understanding. Electronegativity is really based on how the electrons that are in the valence shell and how hard it is to move those electrons away from the nucleus. That makes a lot of sense. We're normally thinking about the electrons moving from one atom to another. So how hard is it to pull an electron in its valence shell away from the nucleus? That's what Allred and Rochot had talked about. And they were able to formulate their own electronegativity scale using the effective nuclear charge of an atom and looking at the covalent radius of that atom. So how hard is it to move that electron? That's effective nuclear charge. How far is it moving? That's connected to the radius. And then there were some other bits that they had to stick on here, a scaling factor. These scaling factors were used to kind of bring it in line with the magnitudes of electronegativity that Mulliken had actually derived. So just bringing them into a factor where they actually scaled appropriately. And again, we do get an absolute scale here, but it does require some data that isn't always available. For example, we may not always be able to easily find the radius of an atom. That might sound a little bit weird, but think about things very far down on the periodic table. Things that we can't measure because they don't have a long lifetime. The transuranics, the synthetic elements that only exist for a little bit of time, they become problematic. So it does require data that may be hard to get, but it is something that's now based on some things that are actually measurable, which is kind of good. And that's really where electronegativity ends. In terms of quantitative scales. There are some other ones out there, but I think these are the three that are most important at this level. They're kind of understandable at this point. The rest of them start diving deeper into other theory that we don't really need at this point. So that is your introduction to quantitative electronegativity. Good piece to know that there are some ways to do that here. As always, we'll talk about these things in class. If you have things you want to know or are confused or need clarity on, let me know and we'll talk about them. Otherwise, until I see you next, be excellent to each other.